Taylor polynomials and approximations. Polynomial functions can be used to approximate other elementary functions such as sine of x, e to the x, cosine of x, and natural log of x. On your calculator, graph sine of x in y1 and its polynomial approximation x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. I've already entered these two into the calculator, and you can find the factorial button by going to the math menu, over to probability, and then it's number 4. Let's go back to y equals. Now we're graphing sine, so let's go to the window, and we can go from negative 2 pi to 2 pi. And we can go by, let's maybe say pi over 4. And sine only goes up to, or down to -1. So let's go to -2 and up to 2. Let's go back. I'm going to go back to y equals, and on the approximation, we'll make this one a little darker so that we can tell the difference. And now let's graph. And the first one it graphs is sine, and then it will graph the approximation. You can see that the approximation, as long as we're centered at 0, the approximation is good, but eventually this approximation will fail. Definition of an nth degree Taylor polynomial. If f has n derivatives at x equals c, then the polynomial p sub n of x equals f of c plus f prime of c times x minus c. Second derivative at c over 2 factorial x minus c squared, and then you'd keep going. You'd have the third derivative of c over 3 factorial times x minus c to the third, and so on. We'd have fourth derivative over 4 factorial times x minus c to the fourth. And you keep going in that pattern. This is called the nth degree Taylor polynomial for f at c, named after Brooke Taylor, an English mathematician. If c equals 0, then p sub n of 0 equals f of 0 plus f prime of 0x. And we keep plugging in 0. Notice how the c is 0, so that just makes this x squared. This is called the nth degree Maclaurin polynomial for f, named after another English mathematician, Colin Maclaurin. Example, find the Maclaurin polynomial of degree n equals 4 for f of x equals e to the 4x. Let's start out by finding what f of 0 is. We're going to plug 0 in because for a Maclaurin polynomial, this is going to be centered at 0. F of 0 equals e to the 4 times 0, which is e to the 0, which is 1. Now we're going to do a fourth degree polynomial, which means we have to take 4 derivatives. The first derivative at 0 is 4e to the 4x. That's the derivative. Then when we plug 0 in, that's going to be e to the 0, that's 1. And then 1 times 4 is 4. The second derivative at 0 is 16e to the 4x, using the chain rule. Then when we plug 0 in, we get 16. Third derivative will be 64e to the 4x. And when we plug 0 in, we get 64. And then finally, the fourth derivative with 0 plugged in will be, let's see, 16, carry the 1, 256 e to the 4x. And then when we plug 0 in, this piece becomes 1, and then we have 256. The polynomial that approximates the function e to the 4x is, we have a Maclaurin polynomial to the fourth degree of x is equal to 1 plus 4x. And this is really over 0 factorial. Let me write that. 0 factorial. This is really over 1 factorial. Then we have plus 16x squared over 2 factorial plus 64x to the third over 3 factorial plus 256x to the fourth over 4 factorial. So the fourth degree polynomial is equal to 0 factorial is 1, so that's 1. 1 factorial is 1, that's 4x. 2 factorial is 2, that's going to be 8x squared. 3 factorial is 6, that means we're going to have 32 over 3. So 32 over 3x to the third. And 4 is 6 times 4, that's 24. If we divide 256 by 2, we get 128 over, let's see, it's 128 over 12. And then we have 64 over 6. We have 32 over 3. So again, we have 32 over 3 x to the fourth. Example, find the Maclaurin polynomial of degree n equals 6 for f of x equals cosine of x. Then use the polynomial to approximate the value of the cosine of 0.1. Let's find out what f of 0 is. That's equal to cosine of 0, which is 1. And then we have to take 6 derivatives. So the first derivative is negative sine of x, and when we plug 0 in there, we get 0. Second derivative is negative cosine of x. When we plug 0 in there, we get 1, but then we get negative 1 with the negative out front. Third derivative now is sine of x, and when we plug 0 in, we get 0. The fourth derivative is cosine of x, and when we plug 0 in here, we get 1. The fifth derivative is negative sine of x, and when we plug 0 in here, we get 0. And then finally, the sixth derivative is equal to negative cosine of x. When we plug 0 in this one, we're going to get negative 1. So the polynomial of sixth degree is equal to 1 plus, we have 0x, and then minus, so this is going to be a minus. We have 1 plus 0x minus x squared over 2 factorial plus x to the third. Well, let's do this. Let's make this an x. This will be the x squared. This is x to the third. 4. This is to the fifth. And this one's to the sixth. So we have the x squared. Next we'll have plus x to the fourth over 4 factorial. And then we have minus x to the sixth over 6 factorial. So there's the polynomial that approximates cosine of x, as long as we're centered at 0. Now the value we plug in order for it to be accurate has to be close to 0, and it's actually 0.1. So let's go to our calculator, and I'm going to turn it on. Let's go to the home screen. We'll quit out of this. And we have 1 minus 0.1 squared, and we're going to divide that by 2. That's what 2 factorial is. Plus 0.1 to the fourth divided by 4 factorial. That's 2 times 3 times 4. That's 6 times 4. We're going to divide by 24. And then we have minus 0.1 to the 6th power, and we need to divide that by 720. And we get a value of 0.995. Let's find out what the cosine of 0.1 actually is. Cosine of 0.1 is 0.995. As a matter of fact, it's accurate to a lot of decimal places. Example, find the Taylor polynomial of degree n equals 6 for f of x equals natural log of x at c equals 1. Then use the polynomial to approximate the value of natural log of 1.1. Let's start out by finding f of 1. We're not going to find f of 0 this time. We're going to find f of 1 because we're centering this function at 1. We have natural log of 1, that's 0. F prime of 1 is 1 over x, which in order to do the derivatives, let's make it x to the negative 1. But either way, when we plug 1 in, we're going to get 1. The second derivative at 1 is, let's look at this to take the derivative, and we'll use the power rule, negative x to the negative 2. Now, the x will go down to the denominator. The denominator will be 1 when we plug the value in, so we're going to get negative 1. Here, look, we have negative 1 over x squared. So when we plug 1 in the denominator, the value is negative 1. The third derivative is equal to 2x to the negative 3. Again, the denominator will be 1, and we get a value of 2 when we evaluate this at 1. So f, the fourth derivative, is negative 6x to the negative 4. Again, the denominator will be 1, and we get negative 6. The fifth derivative is equal to 24x to the negative 5. The denominator will be 1, and we get 24. The sixth derivative is equal to negative 120x to the negative 6th. The denominator will be 1, and we get negative 120. The 0 is going to be the constant, or really x to the 0. This is x to the first, x squared, third, x to the fourth. This will be for x to the fifth, and this is x to the sixth. But we have to keep in mind that this is centered at 1 and not 0. So the polynomial is going to be 0 plus 1x, and this is going to be x minus 1. It'd be over 1 factorial, but we don't need to write 1 factorial. Then we have minus x minus 1 squared over 2 factorial. And then we have plus 2 times x minus 1 to the third over 3 factorial. That's for x to the third. Minus 6 times x minus 1 to the fourth over 4 factorial. That's for the fourth. Then we have plus 24 x minus 1 to the fifth over 5 factorial. And then finally, minus 120 x minus 1 to the sixth over 6 factorial. We're supposed to use this polynomial to approximate the natural log of 1.1. But notice that when we plug 1.1 into all these, 1.1 minus 1 is just going to be 0.1. So that reduces the work we have to do a little bit. So let's go to the calculator and let's enter this in. We'll have 0.1 minus 0.1 squared, and that will be divided by 2, plus 2 times 0.1 to the third divided by 3 factorial. That's 6. We have, that was to the third. Then we have minus 6 times 0.1 raised to the fourth, and we're going to divide that by 4 factorial, which is 2 times 3 times 4. That's 6 times 4. That's 24. So we'll divide that by 24. You got the 6. Now we go to the 24. So plus 24 times 0.1 raised to the fifth. We have to divide that by 5 factorial. And if we multiply this by 5, we get 0. We got to carry the 1, or excuse me, the 2. And that'll be 120. So divide by 120. We could do the factorials if we wanted to, using the math menu. And then finally, minus 120 times 0.1 raised to the sixth. And we will divide that by 6 times 120 is 720. We press enter. We get this value, 0.095. Let's compare that to actually finding the natural log of 1.1. And it is extremely close. It doesn't fail to the very, very end. So 0.095 would be a great estimate for this. Suppose that g is a function which has continuous derivatives, and that g of 2 is 3, g prime of 2 is negative 4, second derivative is 7, and third derivative is negative 5. Write the Taylor polynomial of degree 3 for g centered at 2. So we need the Taylor polynomial. This is going to be a third degree Taylor polynomial. And we know that g of 2 is 3. And then we have minus 4 times x minus 2. So here's your 0 factorial. Here's your 1 factorial. Plus 7 times x minus 2 squared over 2 factorial. And then finally we have minus 5 times x minus 2 to the third over 3 factorial. And so there's your Taylor polynomial of degree 3 centered at 2. Use the Taylor approximation, e to the x equals all this stuff, for x near 0 to find the limit as n approaches 0 of e to the x minus 1 over 2x. We have the limit as n approaches 0. This should probably say as x approaches 0. Let's make them x's. And we can replace e to the x with its approximation, which is 1 plus x squared over 2 factorial, plus x to the third over 3 factorial. And so that's a replacement for e to the x. We still have the minus 1. So we have minus 1 all over 2x. This is equal to the limit as x approaches 0. And we have 1 minus 1, so that's going to be 0. X plus x squared over 2 factorial plus x to the third over 3 factorial, and then all over 2x. Well, every one can be reduced by an x, so let's do that. We have equals the limit as x approaches 0 of, this will be 1, plus x over 2 factorial plus x squared over 3 factorial, and then this is going to be over 2 now. Well, now we can plug 0 in, and 0 over 2 factorial is 0, 0 over 3 factorial is 0, so we have 1/2. Now we did what we were told to do. It says use the Taylor approximation. That's exactly what we did. But if you go back to this, if we plug 0 in here, we get 1 minus 1, that's 0. If we plug 0 in here, we get 0. That's an indeterminate form. So now we weren't supposed to do this, but to check our answer, we could use L'Hopital's. Limit as x approaches 0. The derivative of e to the x is e to the x, and the derivative of 2x is 2. Now when we plug 0 in, we get 1/2. So that's a way to check your answer, but we were told to use the approximation. That's exactly what we did down here. Given that the second degree polynomial a plus bx plus cx squared is the second degree Taylor polynomial for f about x equals 0, what can you say about the signs of a, b, and c if f has the graph pictured at the right? Justify your answer. Well, this is centered at 0, so let's look at its properties around 0. What if we found p sub 2 of 0? That would be a plus 0 plus 0, which would just be a. Well, if we look at the graph, f of a is positive. We are above the x-axis. So a is going to be greater than 0. Now, if we're going to justify this, p of 0 is equal to 0, a, and the graph is above the x-axis. What if we look at the first derivative at 0? The first derivative of this would be bx plus 2c, Let's look at the first derivative of this function at 0. The derivative of a is 0, the derivative of bx is b, and then we'd have plus 2cx. And when we evaluate this at 0, we would just get b. The slope of the line at 0 is positive, so b has to be greater than 0. Now, how are we going to justify this? Well, p sub 2 prime of 0 is equal to b, and the slope of the curve at 0, at x equals 0, is positive. Positive. Let's see, I-V-E. It's positive. Very good. Let's look at the second derivative. Second derivative at 0. And if we take the first derivative, the derivative of b is 0, and then the derivative of 2cx, knowing that this is a constant, is 2c. And this graph is concave down, so c has to be less than 0. Now, how do we know that? The graph is concave down.